Now we'll turn our attention to the actual graphing of rational functions. And this section consists mostly of examples. We'll analyze the graph of rational functions and solve applied problems involving rational functions. The book gives 7 steps. So these will illustrate with examples. They'll be fairly lengthy with all these steps. And in terms of analyzing the graph of a rational function, step 1, factor the numerator and denominator of the rational function. So they'll be polynomials. Definition of a rational function is a ratio of polynomials. Find the domain of the rational function. We could do that as we've done in the past by finding bad points. At this stage, bad things are square roots of negatives and division by 0. Rational functions don't have any square roots in them, so we're interested in division by 0. And once we've factored the denominator in particular, we can see where that's 0, and where that's 0 is where we have problems. So the domain will be all real numbers except for the points where the denominator is 0. Step 2, write R in lowest terms, canceling any common terms in the numerator and the denominator, being sufficiently careful not to lose information, as we'll illustrate in an example. Step 3, locate the intercepts, if any, of the graph. The x-intercepts of P of Q over P of X over Q of X will, of course, be the zeros of the numerator. The y-intercept we find by plugging in 0, assuming 0 is in the domain of the function. If it isn't, then it doesn't have any y-intercepts. It says use multiplicity to determine the behavior of the graph at each of these intercepts. That is, we could analyze whether the graph crosses the axis, the x-axis at x-intercepts, or it touches the x-axis at the intercepts. We'll actually take care of that in a somewhat different way by analyzing sides of the graph. Step 4, find vertical asymptotes. This occurs where the denominator of R in lowest terms is 0. So we have to have simplified with care before we can deal with finding vertical asymptotes. Vertical asymptotes will occur wherever the denominator is 0 after you've put rational function R in lowest terms. There may be places where the denominator is 0 in the original expression of the rational function, yet it does not have a vertical asymptote there. This offer only valid for lowest terms. You've canceled any common terms in the numerator and the denominator. Determine the behavior of the graph R on either side of each vertical asymptote. That too will analyze in terms of whether the function is positive or negative. We know if it has a vertical asymptote, then it's going upwards really steeply or downwards really steeply. And if we know if it's positive, then it must be going upwards to positive infinity, so to speak. And if the graph is negative near a vertical asymptote, then the graph must be going downward to negative infinity, so to speak. And we'll express that in terms of some of the limit notation that the book's introduced that we have not clearly defined, but you will in Calculus 1. Step 5, locate horizontal or oblique asymptotes, if any. We've dealt with this previously. It depends on the degree of the numerator and denominator. Graph the asymptotes using dashed lines, vertical and horizontal asymptotes. Determine points, if any, at which the graph R intersects the asymptote. So graphs can certainly intersect asymptotes. This idea of closer and closer but never gets there is not the case. And that fact that a graph may actually cross an asymptote or touch an asymptote, that's what they're getting at here. So their whole reason in this is to address that misconception that a graph can never take on the value of an asymptotic value. Use the zeros, step 6, of the numerator and denominator of R to divide the x-axis into intervals. Determine where the graph of R is above or below the x-axis by choosing a number in each interval and evaluating R there. So this is where we're determining above or below the x-axis. That's the punchline there. As we've discussed previously, we know these functions are always positive or always negative between the zeros of the numerator and the denominator. That would be between x-intercepts and between vertical asymptotes. And then graph it using all of that information. Let me try to sell you on the book one more time. There's a bunch of good examples in the book, examples 1 through 5. They go through all 7 of these steps, very step-by-step procedure. So I refer you to those, as well as we'll go through and work about 5 examples as well. Okay, so this will take a while because these questions are so long. We're considering kind of different nuances from one question to the next. Let's look at number 8. Follow steps 1 through 7 to analyze the graph of this rational function, x over x minus 1 times x plus 2. Step 1, factor the numerator and the denominator. It's already factored. Find the domain by checking places where the denominator is 0 and casting them out. We have a problem at x equals 1 where this factor is 0, and we have a problem at x equals negative 2 where this factor is 0. Otherwise, we're good to go. So the domain is all real numbers except negative 2 and positive 1. In interval notation, we get something like this. We've taken the whole real line from negative infinity to infinity. We've removed negative 2 and positive 1. The domain. Secondly, was write it in a reduced form, simplify it if possible. There's no common factors in the numerator and the denominator, quite clearly, so nothing can be canceled. It's already in lowest terms. It's already simplified. Step 3 was find the intercepts. For the x-intercept, we'll set y equal to 0. Y is given by the function. The only way a quotient can be 0 is when the numerator is 0 and the denominator isn't. You got to keep an eye on that as well. So we'll set x equal to 0, set the numerator equal to 0, and we get, of course, x equals 0. So the x-intercept is 0. For the y-intercept, we'll set x equal to 0, and we get r of 0 out, just checking we don't get any division by 0 there again. So the y-intercept is 0. X and y-intercept are both 0. This curve passes through the origin. And these are the only intercepts, x or y. If there were more, our technique would have revealed them. Step 4, vertical asymptotes. Vertical asymptotes will occur where the denominator is 0, when r is in lowest terms. It's simplified, it's in lowest terms. So we look where the denominator is 0. These are the points we removed from the real number line to find the domain previously. Denominator is 0 when x minus 1 is 0, or when x plus 2 is 0, this factor or that factor. That is when x equals 1 or x equals negative 2. So these are the vertical asymptotes. X equals negative 2 and x equals 1. Commonly, we'll list the answers in increasing order, left to right. Negative 2 occurs to the left of 1. So I'll list the x equals negative 2 first. It's a good habit. It's not absolutely necessary, but it's a good idea to keep the order in mind when listing these things. So we've got those two vertical asymptotes, horizontal or oblique asymptotes. We had a way to deal with that in terms of degrees. The degree of the numerator is n equals 1 in terms of the notation from a previous section. Degree of the denominator, when we multiply this out, would be 2. Degree 1, numerator, degree 2 in the denominator. When the degree of the numerator is strictly less than the degree of the denominator, then a rational function has a horizontal asymptote of y equals 0. So now we've got the vertical asymptotes and the horizontal asymptotes. If this is happening too fast, you might want to pause right here and go back and look when we were discussing, in particular, horizontal asymptotes, and excavate where we discussed that in terms of the degree n of the numerator and the degree m of the denominator. Step 6, where is this positive and where is it negative? So what we'll do is use the zeros of the numerator and the denominator to divide the x-axis into intervals. That was step 6. X equals 0 is where the numerator is 0. -2 and 1 is where the denominator is 0. I need those in order, left to right, -2, then 0, then 1. So we'll take the whole real number line, remove -2, then 0, then 1, creating these 4 disjoint intervals, disjoint open intervals. All right. Now, this function, being a rational function, being continuous, will have the same sign throughout this interval, and this interval, and this interval, and this interval individually. It can't change from positive to negative unless it either goes through 0 or we have a vertical asymptote. Here's where it goes through 0, and these 2 points are where it has a vertical asymptote. So if it changes signs, then it does it at one of those 3 points. So all we got to do is check a test value from each of these 3 intervals and see if the function is positive or negative at that test value. If it's positive at that test value, it's positive throughout that interval. So we'll make a little table next with the intervals listed on the top. We'll choose a test value C. You will use this technique in calculus as well for things more general than rational functions and with another agenda in mind, but this same technique you'll use in calculus. Choose a test value, call it C. Pick a number, any number from the interval -∞ to -2. Let's pick -3 because it's kind of small and it's in that interval. Can't use -2. It's an open interval. It doesn't include its endpoint. -2 to 0, pick -1. It's the obvious choice, though you could choose anything you like between -2 and 0. 0 and 1, I got to choose a non-integer, so we'll choose a half. 1 to infinity, let's choose 2. Now we will plug these into the function. I'm going to abbreviate the arithmetic here a little bit. We've plugged each of these C values into function R and computed R of C. Now I haven't simplified in what's written here because I'm ultimately not so much interested in the value as I am the sign of the value. You'll plug in -3, we'll get a -3 in the numerator, and in the denominator, we'll get a -4 times a -1. If you'll look at the factors, we've simply plugged -3 in and produced these numerical results. And yeah, that simplifies to -3/4, but I'm really only interested in the fact that it's negative. All I got to do is count negative signs to determine that. Involves a product or quotient of 3 negatives. That means the result will be negative. It's -3/4 if you're into the numerical values. I don't so much need the numerical values, really just need the fact that this is negative. So that tells you the graph is below the x-axis throughout this interval. Next interval, we'll plug -1 in. So looks like we get a product of 2 negatives, well, quotient of 2 negatives. That yields a positive value. By the way, it's +1/2. The 1/2 I'm not so interested in, but positive I am. And so the graph of this function is positive throughout this open interval. That is, it's above the x-axis throughout this interval. Next interval, plug in a half. And we get out a positive divided by a negative and another positive. That'll yield a negative value. That value is -2/5, I think. It doesn't matter. It's negative because of the single negative factor. And so the function is negative throughout this interval. And similarly, we'll plug test value of 2 in. It looks like we get +1/2 out. Anyhow, positive. So R is below the x-axis where we got the negatives. That was here and here. So -∞ to -2, union 0 to 1. R is above the x-axis where we got positive out. So that would be here, union here, -2 to 0, union 1 to infinity. So that takes care of the positive negativeness above the x-axis, below the x-axis equivalently. From step 4, we still had one loose end. We still had a concern over whether the asymptotes went up or down. And now we got the information to deal with that in terms of this positive negativeness. In step 3, they also asked, and it's not addressed in these solutions, about where the function crosses the x-axis. It had a vertical asymptote at -2, so there's no x-axis conversation there. At +1, similar result. But the function was defined at 0, and the value was 0. It was the intercept. And it's changed from positive to negative. So if you wish to address that, since the function is defined at 0, the point between these two intervals, and it changes from positive to negative, that tells you the curve crosses the x-axis at that x-intercept. That'll be implied by all the other information, though. The asymptotes, let's see what we can get out of this chart in terms of asymptote information. Now, this function, it's negative from -∞ to -2, and it has a vertical asymptote at -2 that we explored above. So what's it doing on the negative side of -2, to the left of -2? How is this vertical asymptote behaving? Is it going up to positive infinity or down to negative infinity? Well, if the function values are negative, then it must be that the asymptote is a vertical asymptote that goes down to -∞, so to speak. The book introduces some notation in one of their figures from, I think, from a previous section. They use the symbols. The limit as x approaches -2 from the negative side of r of x equals -∞. All right, here's how to make sense of this. We have not formally defined this. You will in Calculus 1. What this means is, at the vertical asymptote -2, when we come in towards -2 from the left, from the negative side, so that little superscript of a negative sign means we're coming from the left, from the negative side, the function's going down to -∞. We knew the function was negative on this side of -2. R is negative in this interval. If it's negative and it has a vertical asymptote, then the function must go downward on that side of -2. On the other side of -2, R is positive. R is positive on the interval -2 to 0. R still has a vertical asymptote at -2. So what happens on the other side of that asymptote? What is the limit as x approaches -2 from the positive side? That is, from the right-hand side where we're involving numbers greater than -2. Function's positive and has a vertical asymptote. It must go up to positive infinity. Similar analysis over here at 1. It was negative on the left and positive on the right. It must go down on the left, the negative side, and it must go up on the right, on the positive side. You might want to digest that. It's a lot easier once you see a picture, but we're trying to create the picture. So we've got to take this positive, negative information and convert it into behavior near the asymptotes. Here's all that information. Let's start with asymptotes. First, we had a horizontal asymptote of y equals 0. That was because the numerator was degree 1 and the denominator was degree greater than 1. It's 2. We had vertical asymptote at x equals -2. So next we'd insert the vertical dotted line. We also had a vertical asymptote at x equals 1. Hey, -2 and 1, those are the values that made the denominator 0. We did a sign test and saw that the function was negative over here. Well, if it's negative and has a vertical asymptote, it must be going downward. And that was what we explained on the previous slide. But negative means below the x-axis. Vertical asymptote means it has to get really steep. It must go downward, when it couldn't go upward, or else the function would be above the x-axis. And we know it's below the x-axis. In the next little interval, from -2 to 0, we saw the function was positive and above the x-axis. It had an intercept at 0. The x and y-intercept was 0. On this side, also vertical asymptote. Vertical asymptote and function is positive. Then, if we view how the function behaves in this vertical asymptote from the right-hand side, the positive side, it must go up. Next interval, 0 to 1. The function was negative, below the x-axis. Has a vertical asymptote, must go down. Next interval, 1 to infinity. Function was positive, above the x-axis, must go up for that vertical asymptote. And also, to satisfy the conditions of the horizontal asymptote, we must have it do something like this. Could the function have maybe gone down below that asymptote and come back up? No, because we know the function is above the x-axis. It couldn't have dipped below. Similarly over here, it couldn't somewhere have gone above and come back down. I know it comes down and gets close to this horizontal line, but it could wiggle some more. Well, it doesn't wiggle so much that it crosses that asymptote over here. We know that by the above, below the x-axis stuff. Does it ever actually cross the asymptote? Actually, it does it at the x-intercept. It crosses the asymptote. And we didn't describe that verbally in the comments that we went through, but this actually does cross its horizontal asymptote. It does it right there. I bet you that's what the graph looks a lot like. Here's some things we can't, with our current knowledge, eliminate. Okay, I know this doesn't go down and cross the axis because the sign test would have told us, the x-intercepts would have told us. How do you know this function doesn't wiggle some more? Maybe it goes down and then it goes up, and then it goes down and then it goes up, and then it horizontally approaches the x-axis. How do you know it doesn't wiggle more up here? I know it has these asymptotes, but we don't have any knowledge yet that tells us this doesn't maybe wiggle a little bit more. Know what I mean? If I knew things about maxes and mins, and I do, that's for polynomials though. If I knew things about maxes and mins, I could maybe eliminate that wiggles more concern. This is a simple function, and this is a pretty good graph of it. But there's certain behaviors that we can't eliminate with the knowledge we have. And you'll have the knowledge in Calculus 1 to show, no, it doesn't wiggle more. If it wiggled more, the techniques you have in calculus, they'd tell you about it. But this function, this graph, certainly satisfies all the conditions that we know about the graph in terms of asymptotes, in terms of above and below the x-axis, and in terms of intercepts. So that graph's got to be pretty close to what this function looks like. Let's do another one. Same story, different function. Here we've got g of x is x squared minus x minus 12 over x plus 1. Okay. Step 1, factor numerator and denominator. X squared minus x minus 12, the numerator factors into x plus 4 times x, x plus 3 times x minus 4. FOIL it out and you'll see, in fact, that's true. As we described in one of the appendices, I look for two numbers that multiply to give negative 12 and add to give negative 1, the coefficient here. Let's try 3 and negative 4. They multiply to give negative 12, and they add to give negative 1. So that's correct. So we can factor g, the numerator that's given, and write g of x in this form. It's in lowest terms. There's nothing to cancel. There's no common factors in the numerator and the denominator. We'll see one of those later. The denominator can be 0, so that's a problem. So if we look for the domain, we look for places where the denominator is 0. That occurs at x equals -1. Everywhere else we're okay. So the domain of this function is all real numbers except for -1, written in interval notation as given here. Step 2, write the function in lowest terms. It's already in lowest terms. There was nothing to cancel, so that takes care of step 2. Step 3, intercepts. For the x-intercepts, set the function equal to 0. The only way this quotient can be 0 is if the numerator is 0 and the denominator isn't. That will imply x equals -3 and x equals +4. -3 and +4 will yield the x-intercepts. To find the y-intercept, we'll set x equal to 0, plug 0 into the function. Looks like we get -12 out. So the y-intercept is -12. This we've been doing for a while with the intercepts. Step 4, vertical asymptotes. Vertical asymptotes will occur where we have division by 0, where the denominator is 0. The denominator is just x plus 1. So we got a problem at x equals -1. It's a rational function. We've got a vertical asymptote at x equals -1. Does it go at -1 up on both sides? Does it go down on both sides? Up on one side, down on the other, up on the other, down on the one? We'll figure that out using a sign test. So we're not entirely done with step 4, but we'll take care of it when we do the sign test. Step 5 was horizontal or oblique asymptotes. In this case, the numerator is degree 2. Because of the 2 right there, the denominator is degree 1. In the event that the numerator is degree 1 larger than the degree of the denominator, we get an oblique asymptote. Y equals ax plus b. To find the a and the b in that oblique asymptote, we simply do long division. So we take the numerator, x squared minus x minus 12, and divide it by x plus 1. I leave it to you to grind through this division. We've done this before as well. But we get that the quotient is x minus 2. The remainder is -10. Well, the quotient is the oblique asymptote. So we get for the oblique asymptote y equals x minus 2. So we'll graph that when it comes time to graph as well. Step 6, above or below the x-axis. So this is where we'll do the sign test stuff. We'll take the whole real number line. We'll remove places where the numerator is 0, -3 and 4, -3 and 4, and places where the denominator is 0, that was at -1. So we'll take the real number line and remove -3, -1, and 4. Just a quick warning, make sure you list those numbers in order. Don't use the -1 first and the -3 second. You won't be creating intervals. You'll just be creating nonsense. Be careful. It's easy enough to mess up. List them in order, lesser to greater, as you remove them from the real number line. And so we need to consider these 4 intervals similar to what we did previously. Let me speed this up a little bit. Feel free to pause and double check the arithmetic and convince yourself it's correct. But what we're going to do is choose a number, any number from each of these 4 intervals. Let's use -4, -2, it's the only integer in that interval. Let's use 0. There's several integers in that interval, but I prefer arithmetic with 0 because it's easier. 5 is in this interval, and it's a small integer. Plug these into the function, producing these expressions. You simplify them if you want. I really just need the signs of them. Here we've got negative times negative divided by negative. That'll result in a negative. Here we've got positive times negative divided by negative will result in a positive, and similar for the other two. Well, this positive negative stuff tells us where the function is above the x-axis, that is where it's positive, or below the x-axis, that is where it's negative. Below the x-axis, where it's negative, that would be here and here. So we'll take the union of those two. Above the x-axis, where it's positive, the function is positive, would be this and this, union together. There's where we've got the positive and the negative. This we're going to use to analyze the vertical asymptote. We had a vertical asymptote at -1. G is positive from -3 to -1. So to the left of -1, nearby at least, this function's positive. So it must be on that side to the left, the negative side of -1, the function must be going up because the function is positive there. To the right of -1, the function is negative. So the function must be going down on that vertical asymptote as x approaches -1 from the positive side. Since the function is negative, the function must be going downward, which we write symbolically like this. One more time, x approaches -1 from the positive side. The limit of g of x is -infinity. Graphically, that simply means we got a vertical asymptote that goes down on that side, on the positive side of -1. On the negative side of -1, it goes up. And that's all based on this positive negativeness that we have in the table. So we're set to graph asymptotes, one vertical asymptote, one oblique asymptote. So vertical asymptote at -1, the function went up on the left and down on the right, right? That's what we deduced from the fact that the function is above the x-axis here and below the x-axis here. It's -1 to 4. We had it below the x-axis. Above the x-axis on the right and below the x-axis on the left. So the graph must look something like this. Here's a graph of the oblique asymptote, slant asymptote. I should put the formula on it, actually, but I'm trusting I got that right. It passed through this point. It looks like I can't even determine the slope because I haven't calibrated the y-axis. We had the equation for it. I could have done a better job of labeling it at least. But it's an oblique asymptote, not a horizontal asymptote. And once we sketch that in, then the idea is we had a y-intercept and two x-intercepts. I'll just try to flesh out the graph so that it has the appropriate asymptotic behavior. That's the only thing beyond these 3 points that we know for sure. Well, I know above and below the x-axis, I guess, and I know the intercepts and the asymptotic behavior. So I suspect the graph looks a lot like this. How do you know it doesn't wiggle some more in between here? I don't. I bet it doesn't because it's not a complicated graph, but I don't have the knowledge to determine whether it wiggles a lot more. I know it remains below the x-axis, but how much it wiggles, got nothing on that. I will in calculus 1. So there's the graph of that one, and the illustration. In this case, the point was the oblique asymptote. Let's do another one. Here is a rational function, x squared plus 3x minus 10 over x squared plus 8x plus 15. Find the domain. Factor the numerator and the denominator. So we need to factor x squared plus 3x minus 10. I need two things that multiply to give 10 and add to give 3. How about 5 and -2? X squared plus 8x plus 15. I need two things that multiply to give 15 and add to give 8. How about +5 and +3 this time? So take your time in digesting that factoring. It's correct. So kind of trust me if you just want to see the new stuff. But we'll factor the numerator and denominator and produce this. So here's a factored version of R of X. That was step one. From this, we see the denominator can't be 0. This one's a little more subtle. Denominator can't be 0. So X cannot be -5 and X cannot be -3. Now, I know there's something here that we could cancel, but we're going to be very careful with that. The denominator can't be 0. Here's what the denominator is. Well, then X can't be -5 and X can't be -3, or else the denominator would be 0. Other than that, we're good. So the domain consists of all real numbers except for -5 and -3. So we'll take the real line, remove -5, remove -3. There's the domain of the function. Next, we're going to look at this lowest term stuff. Write R in lowest terms. But be very careful to preserve the information about the domain. We discussed this in one of the appendices. Can you cancel those X plus 5s? If you're careful, yeah. X plus 5 divided by X plus 5, that's always 1, right? Well, not when X equals -5. Remember, X can't be -5. If we simply cancel these and write this, and that's all, we got a problem. This function doesn't equal this function. This function's defined at -5. This function isn't. We get division by 0 at -5 in this function. In this function, we don't. So I can't write just this. What I can do is write this along with the disclaimer that X can't be -5. X can't be -5 in this function because of the X plus 5 in the denominator. X can't be -5 in this function, including the statement, because we said X can't be -5. You leave this off, you've changed things. This is subtle, but it's part of what makes all of calculus work. So let's get it right early on. So we have equality of this function and this function, along with the fact that X can't be -5. So here we have R of X written in lowest terms. We had to add a little statement there. So the examples are getting more sophisticated. Okay, let's find intercepts. We'll deal with R in lowest terms. It'll be simpler. Remember, that comes with this disclaimer of a sort that X is not -5. But we'll get R of X then as X minus 2 over X plus 3. If we're looking for X-intercepts, we'll set that equal to 0 with this in the back of our mind. Maybe back of our mind's not a good place, but we write it explicitly right there. The only way the quotient can be 0 is if the numerator is 0. So this implies X equals 2. And so X-intercept, we set Y equal to 0. We found X equals 2. The X-intercept is 2. Y-intercept, we'll simply plug X equals 0 in. By the way, that satisfies this condition. Plug 0 in, we're left with -2/3. So the Y-intercept is -2/3. Asymptotes. All right. Asymptotes. This hasn't been an issue previously, but it was explained in step 4. To find the vertical asymptotes, we set the denominator of R in lowest terms equal to 0. Here is R with that disclaimer in lowest terms. The denominator is X plus 3. So we'll set the denominator X plus 3 equal to 0, and that implies X equals -3. We've got a vertical asymptote at -3. We don't have a vertical asymptote at -5. -5, granted, is not in the domain of the function, but we don't have a vertical asymptote there because when we put R in lowest terms, we're not concerned with X minus 5, or excuse me, with the X plus 5 in the denominator. Let's go back to the lowest terms. When we look at this in lowest terms, set the denominator equal to 0. This is the only thing that matters. The fact we get 0 in the denominator when x is -5, well, that's a bit of a different story. You find the vertical asymptotes by taking the thing in lowest terms and dealing with that. So that's where the x equals -3 as a vertical asymptote comes from. And there's some additional explanation about why x equals -5 doesn't yield a vertical asymptote. Check out theorem 2.2.a, I guess, in section 2.2. But it says right there in step 4, you find vertical asymptotes based on the form of the rational function in lowest terms. Horizontal asymptotes. We had numerator and denominator were both of degree 2 in the original function. If you wish to deal with the original function, we could just as easily deal with a simplified version. But if we go back to the original function, so let's blink back to the previous slide. Here's the original function. Degree 2, coefficient is 1 in both the numerator and the denominator. When the degrees are the same, we have a horizontal asymptote of the form y equals a constant. And that constant is this coefficient divided by this coefficient. So it's 1 divided by 1 in this case. Leading coefficient in the numerator divided by leading coefficient in the denominator, and we get that. So that gives us a horizontal asymptote of y equals 1. We had the vertical asymptote above of, wasn't it x equals -3. Step 6, let's do the sign test deal. So we'll take the whole real line. We'll remove the zeros of the denominator, which were -5 and -3. -5 and -3 get removed there. The numerator had zeros of -5 and +2. We already removed the -5, so the +2 gets removed as well. So we'll remove those 3 points where either the numerator or the denominator is 0. This yields 4 intervals. We'll do a sign test on each of those. Let me speed things up a little bit because this is repetitious, but feel free to pause and pause the video, convince yourself that these statements are correct. We'll choose a test value from each interval. We'll plug it into the function. That will tell us positiveness or negativeness, that is above the x-axis or below the x-axis for the graph of the given function. So we've got negative on this interval, so below the x-axis on this interval, positive on the other intervals, so r is above the x-axis on the union of the other 3 intervals. We still have an asymptote, a vertical asymptote to process. That vertical asymptote was at -3. To the left of -3, on the interval -5 to -3, r was positive. Well, if it's positive and it has a vertical asymptote, it must be going up. In the symbols we had, the limit as x approaches -3 from the negative side, from the left, of r of x equals positive infinity, if you like. They don't usually put the plus sign on the infinity. On the interval -3 to 2, that is the behavior of r to the right of -3, to the right of where that vertical asymptote is. Function is negative, so it must be going down. The limit as x approaches -3 from the positive side, from the right, must be negative infinity. It goes down on that side. So let's see. We're dealing with graphing this function, which we can rewrite simplified like this. Got this x equals x does not equal -5 disclaimer over here. This is a little extra bit of work in this one because this one's so exotic. Now this function, x minus 2 over x plus 3, right? I didn't say anything about the not equals to -5 thing. This is a different function, but this function is the same as the r of x function everywhere except at -5. Well, what does this one do at -5? If you plug -5 into this function, you're going to get out, looks like you get out 7/2. -5 minus 2 is -7. -5 plus 3, that's -2, produces, yeah, positive 7/2. But this function contains the point -5, 7/2. This one doesn't, because this one's not defined at -5. You're not allowed to plug -5 into this function because it produces division by 0. Or we wrote it explicitly right there to reflect that division by 0 concern. This one doesn't have that concern. And these are the same everywhere except at -5. This function passes through the point -5, 7/2. Well, that means this function is going to try to do that because it does the same thing this function does, just at -5, they're different. I've worded it as the graph of R is the same as the graph of this function here, G, except that it's got a hole punched in it at the point -5, 7/2. I would read this more in a calculus setting as the given function, it tries to pass through this point -5, 7/2, but it can't because it's not defined at -5, as you can see from the denominator. As long as x isn't -5, these cancel, it's just 1. But at -5, you can't have an at -5 for this function. So the function's not defined at -5. To indicate that, we'll draw a little hole punched in the graph of the function. And we've seen examples of these in the past. This is the first time we've algebraically encountered it. Okay, we had a vertical asymptote of -3, a horizontal asymptote of 1. I draw those as dotted lines first. We had the intercepts, Y-intercept of 0, -2/3, X-intercept of 2. We knew the function was above the x-axis on this interval over to -3. So it must do something like this. In particular, it goes upwards, as previously discussed. From the left, the limit as x approaches -3 from the negative side is positive infinity, it goes up. From the other side, it went down because the function was below the x-axis. So that accounts for the vertical asymptote behavior. The horizontal asymptote, it must get close to and stay close to that horizontal asymptote on the far left and on the far right. We got the intercepts. We've got it below the axis here. It switched over to above the axis. By the way, it crosses the x-axis at x = 2. And the graph of this function must look a lot like that. The exotic behavior is that it's got a hole punched in it right there. That's because of this x + 5 over x + 5 thing. It effectively punched a hole in the graph at that point. Function's not defined at that point. It wants to pass through that point. It tries to pass through that point, but it fails because the function's not defined at -5. It's not a continuous function at this, near here. I'd have to pick up my pencil because it's got a hole in it there. And it's all caused by that x + 5 divided by x + 5 thing. This foreshadows some things you'll see in calculus related also to the idea of a limit of a function. So this is actually a fairly important example with an eye towards the future. Let's do it backwards. So here's a graph, and they ask you to find a rational function, capital R, that might have the given graph. Okay, we've done these kinds of things before, I think. Here, we can't give a unique answer, as it says more than one answer might be possible. We could maybe do horizontal and maybe vertical stretches of whatever we get, multiply the given answer we're going to produce by probably a positive constant and get other potential answers. So we'll do it in the simplest way we can. Things we know: vertical asymptote at -1, vertical asymptote at +1, horizontal asymptote of 0. Just like when we graphed them, probably the first thing you did was draw the asymptotes. So let's observe that first. What's that tell you? We must have an x + 1 in the denominator, and we must have an x - 1 in the denominator. How about the horizontal asymptote of 0? must be the degree of the numerator is less than the degree of the denominator. That's when you get horizontal asymptotes of y equals 0. An intercept, okay, that'll tell you something about the numerator right there. X minus 0 must be a factor of the numerator. Let's start with that information. The additional information is where it's above and below the x-axis. But starting with the fact that we've got vertical asymptotes at -1 and 1 tells us the denominator, let's write this as p of x over q of x because it's a rational function. The denominator q needs to have factors of x plus 1 and x minus 1. X plus 1 being 0 under these conditions, x equals -1, and x minus 1 being 0 under this condition, x equals 1. Since the y-intercept is 0, then the numerator must have a factor of x minus 0, a factor of x. Any other factors in the numerator? No, because there weren't any other intercepts. No other intercepts, no other factors in the numerator. We could have this one repeated, but we couldn't have different factors in the numerator. The graph of R has y equals 0 as a horizontal, asymptote. Little boo-boo there. It's the x-axis. The horizontal axis is a horizontal asymptote, but that should read asymptote. I will correct that little typo. When y equals 0 is a horizontal asymptote, then the degree of the numerator must be less than the degree of the denominator. Q must be of greater degree than is P. If we take P of x to be simply x, degree 1, and take Q of x to be, we know it has these two factors and no others because there weren't any other vertical asymptotes, but these could be factors of higher multiplicity. If we take these to be the only factors of Q of x, we get Q of x is x squared minus r, then we'd have the rational function, let's call it r sub 1. So we're just using the asymptote information so far. We'd have x over x squared minus 1. Does that work? It's got the right domain. The only place it's got problems are plus or minus 1, where that function had vertical asymptotes. And that function was defined everywhere else. It's got the right y-intercept. Plug x equals 0 in, and we get out y equals 0. Let's set y equal to 0. We get out x equals 0 as well. It's got the correct intercepts. And it's got the correct asymptotes. It's got the correct vertical asymptotes. Are we good with a horizontal asymptote? Degree of the denominator is greater than the degree of the numerator. 2 is greater than 1. Yeah, we're good. So this has the correct asymptotes, the correct domain, correct intercepts. The only thing that could go wrong is the above the x-axis, below the x-axis stuff. So let's see what happens there. Let's plug in 3. y3, let's go back and look at the graph. At 3, the function was negative. So let's plug in 3 and see if we get a negative out. If we plug in 3, we'll have to this function, we'll have 3 divided by 3 squared minus 1. That's 3/8. That's positive. We see from the graph, r of 3 is negative. It was below the x-axis there. So that's wrong. Well, let's fix it by throwing a new negative sign in. So for r, let's change the sign of r1 and try negative x over x squared minus 1. That'll change the above and below the x-axis stuff. So let's try that for r. So you can see how we did it in steps. First, using the asymptote information, we produce this asymptote and intercepts. And then checking effectively checking the above or below the x-axis stuff, the positive negative stuff. And we were wrong about that. So we'll change it. Now, let's go through the intervals. -∞ to -1, there was a vertical asymptote here. -1 to 0, there was an intercept here. 0 to 1, there was a vertical asymptote here. And 1 to infinity. Let's try this function out, take test values from each of those, plug them in, we get positive, negative, yielding above the x-axis and below the x-axis as given by the intervals, and that's what the picture was. So let's go back and check. Below the x-axis on the right in the interval -1 to 0. Above the x-axis on the left and between 0 and 1. Let's go back and look at the picture for that. Yeah, above the x-axis on the left and between 0 and 1. Below the x-axis on the right and between -1 and 0. That's exactly what we had. That graph satisfies all the conditions that we know how to check. That equation satisfies all the conditions given in the graph. So starting with the graph and then determining the equation. There's a lot of the stuff we just did, only backwards. We started with asymptote information. That gave us the form of the function. Then we used the above, below the x-axis, and that gave us a plausible formula for the function r. So r of x equals negative x over x squared minus 1. That satisfies all the conditions we know. Give me another function. We could multiply the whole thing by 7, put a 7 in the numerator. That would vertically stretch things. We probably couldn't tell that it stretches things too well from the picture we had, but it would still satisfy all the same asymptote conditions, all the same intercept conditions, and all the same above and below the x-axis conditions. We could play around with the order of these factors very carefully. We'd have to maintain parity. Instead of using x, we could potentially use x cubed. If we did that, we'd probably have to manipulate the denominator to keep the same horizontal axis. There's lots of other correct answers. This is the easiest one though. So this is kind of probably the book's intended solution. So there is taking a graph and using the information related to asymptotes, intercepts, and above and below the axis ideas to take a guess at what the equation of the function might be for the given graph. Let's do an application. Okay, after all of that, this is relatively easy. It says United Parcel Service, UPS, has contracted you to design an open box with a square base that has a volume of 5,000 cubic inches, as given here. So they want a square base. They've labeled it for us, say x by x, so the base is square. The height is y. The volume is 5,000 cubic inches, and for some reason it doesn't have a top. Question is, express the surface area, S, of the box as a function of x. Using a graphing utility, I don't care much for these, but I'll put one in these sample exercises. We'll use something called Wolfram Alpha. It's free, it's straightforward. It'll graph for us. It'll do a lot of stuff, in fact. Graph the function in part A. Graph S as a function of x. Part C asks, what is the minimum amount of cardboard that can be used in constructing the box? So we haven't talked extrema in a little while, and we don't have a good way of finding extrema, not in this case. We'll use the graph and do our best. What are the dimensions of the box that minimizes the surface area? So they're asking what is the minimum and where does it occur? It's one of those what and where type questions in terms of extrema. And part E, why might UPS be interested in designing a box that minimizes surface area? Okay. First, they want surface area as a function of x. From the figure, we got a box of length x, width x, and height y. They gave us this picture, so we're good there. The volume of the box, in terms of those symbols, would be x times y, length times width times height. It'd be x squared y. And your total volume is 5,000 cubic inches. So you have the relationship, volume is x squared y equals 5,000 cubic inches. X and y must be measured in inches. So we can solve for y in terms of x. divide both sides by x squared, and you'll see that y equals 5,000 over x squared. I want y in terms of x because they've asked us to find the surface area in terms of x. So I give the verbal cue of what you're up to there. We want things in terms of x. We want y in terms of x. We want to find the total surface area. Well, the surface area would be the bottom of the box, which is x squared in area, plus 4 times the area of the sides. The sides are x wide and y tall. So the surface area of this front face is x times y. The surface area of all 4 of those faces is x times y. So the total surface area is the bottom, x squared, plus the faces, 4xy. But this has x's and y's in it, and they just wanted us to do things in terms of x. Well, conveniently, we know y in terms of x. So we'll substitute this in for y, eliminate the y, and then we'll have s in terms of x. So x squared plus 4xy becomes x squared plus 4x, 5,000 over x squared, since that equals y, which we can simplify a little bit as x squared plus 4 times 5,000, 20,000, and cancel one of these x's. X can't be 0. Of course, x can't be 0. If x were 0, then you ain't got much of a box. And we get the surface area as x cubed plus 20,000 divided by x. So they wanted surface area as a function of x. There it is. It's expressed in square inches, which is not immediately clear, but we're measuring distances in x and volumes in x cubed. We're measuring distances in inches and volumes in cubic inches. So areas are in square inches. Graph it, eh? All right. I'm going to go to some software called Wolfram Alpha. If you'll go to the online notes, there's a hyperlink. These red fonts indicate there's a hyperlink to the Wolfram Alpha website, and you can, it's fairly intuitive. You can tell it to graph and give it the function, and it'll produce a graph and additional information. So using Wolfram Alpha, a graph of S of x looks like this. They've given some things over here for x negative, which we're uninterested in because for us, x is a distance. So we're really only interested in what happens for x positive. Notice when x is really small, looks like the surface area is really big. Yeah, if x is small and the volume is 5,000 cubic inches, then the y parameter must be really, really, really big if x is really small. And that's what's resulting in a large surface area. So we get a graph that looks like this. They ask us to guess, based on this graph, what the minimum is. And it mins out. In fact, I think Wolfram Alpha probably tells you this. Has a minimum somewhere over here. Hard to say. It looks like it's a little bit bigger than 20. 22 is right here. If you can see the little calibrations, it's clearer if you'll download the notes. It looks a little bit less than 22. But somewhere around here, the minimum marked with a dot occurs at some value slightly less than x equals 22 inches. Okay, that's pretty sloppy stuff. In fact, in calculus, you'll have a way to find the exact value of where that minimum occurs. Wolfram Alpha knows calculus. It's very clever software. In fact, the minimum occurs at 10 times the cube root of 10. It's about 21.5-ish inches. So it is a little bit less than 22. And the picture, the graph seem to indicate that. So that's consistent. But let's go ahead and take Wolfram Alpha's output of 10 on the cube root of 10. That's where the minimum is. You know, I don't like this eyeballing it and guessing stuff, or depending on software. You will have a technique to do this in calculus and to find these precise values. They wanted to know, where does the minimum surface area occur? It occurs where x equals, well, this, 10 on the cube root of 10 inches. What is that minimum? Well, we'll take that value plug it into the function S, which gives surface area, grind through the numbers, produce something of this sort, approximately this amount here, 1,392.477 square inches is what we get for the surface area. We can also, based on that X value, find the associated Y value. I've given all of these values precisely, and then then numerical approximations to 3 decimal places in terms of inches, or so error there, that should be square inches. Oh, it says square inches, it's there. So inches for X and Y, and square inches for the surface area. Why would UPS be interested in this? To minimize weight by minimizing the amount of cardboard they use, for example. Minimize materials to minimize the cost of producing such a box. So minimization of weight, minimization of material. You're going to fill this box and move it across the country, so that impacts, the weight of it impacts the fuel spent in moving it. So for reasons such as that, really to minimize cost. Why do you want to have an open top box? I got no clue on that. If it's some kind of crate that they're stuffing other boxes in. But that's the problem they gave us. There's a way to approach it using some software. I prefer more analytic things, and you can easily get software to work lots of these problems and output these approximations. But we need something fairly sophisticated to go through and find the precise values. We don't have it yet. Calculus is quite sophisticated, and you'll have it in calculus. So that takes care of graphing of rational functions. What comes next is we'll look at inequalities related to rational functions and inequalities related to polynomials. I'll see you in the next section. Have a nice day.